Good day, ladies and gentlemen. My name is Ibrahim Abdulhalim, and I will be talking about miniature photosensing solutions, miniature systems, such as surface plasmon resonance, spectroscopic solutions, polarimetric imaging, interferometric, and some vision components or systems. The main work is originated from my research. I'm a professor at Ben Gurion University, and the company that I am representing here was established by me and trying to promote several of these miniature solutions, such as the SPR and other miniature instruments. First of all, I would like to thank Prof. Namjoon for inviting me to give this presentation. Okay, and we'll start directly to talk about miniaturization, particularly system miniaturization, why we need that and what is the motivation. So the first motivation is the fact that there are so many miniature optical components and optoelectronic components, which actually attracting us to make more miniature devices and systems. So the miniature cameras, imaging sensors are one example. Polarimetric sensors, which are coming in chip form. Of course, light sources, lasers, laser diodes, LEDs, and so on. Some of them even high power. Raman probes. Of course, in electronics, we can use these miniature basically processors, computers like the Raspberry Pi, and embedded within a system. Of course, the cell phone is the horse for miniaturization because it's already including the processor, the display, the wireless communication, the ability to connect it, a camera, a light source, and ability to write application. So it is an excellent device for miniaturization photonic instruments. Of course, we can also talk about small miniature other computing devices like laptops, small laptops, or tablets, and so on. In optics, there are so many other components which are suitable for miniaturization, such as micro-optic components, microlenses, fibers, waveguides, and so on. As mentioned, spectroscopic solutions can come in a variety of ways. Even the standard spectrometers, which use a grating and a camera or a parallel detector, array of detectors, are coming now in a miniature format. As you see here, variety of sizes can be on the size of your palm. And some of them are coming for imaging, such as pixelated devices, which include many pixels able to detect at many wavelengths on the expense of resolution, of course. And you can also talk, of course, about tunable filters, which can come in a variety of ways to perform spectral imaging, and we'll be mentioning some of these. Of course, there are a variety of electro-optic components. The most prominent are liquid crystal-based devices because they are miniature, they do not require power or very low power, They have very large electro-optic effect. For example, the liquid crystal spatial light modulator used in many applications, digital holography, imaging, aberration corrections, and so on and so on. Tunable lenses are coming on the way. Some of them already exist. They can be made from deformable, like liquid lens, static approach, or tunable liquid crystal-based devices. And of course, there are a variety of miniature sensors which can be used to give us a variety of functions. And there is more, of course, for motivation. For example, the fabrication at the micro and nano scale these days is available using a variety of techniques, E-beam lithography, DBUV, X-ray, nano imprinting, 3D imprinting, and so on. Of course, there are a variety of new photonic components or structures, such as plasmonic or photonic crystals, and so on, which allow us to obtain highly strong electro-optic or photonic effects. For example, within plasmonic enhancement of the local electromagnetic field, we enhance the fluorescence, Raman scattering, or infrared spectroscopies, which allow us then build a small miniature spectroscopic device, because the signal now is very strong. So we don't need this large spectrometer or detector. And of course, we can design, we can simulate quite easily these days using already existing softwares or algorithms such as computational imaging, compressed sensing, AI, neural nets, and so on. And the other motivation is the need for that. There is a market, and there is a big market, a lot of money, but also there is a need for health. A well-known problem now is COVID-19. Then there is also a lot of requirements for early diagnosis, fast pathogens detection of toxic materials, biomarkers, and so on and so on. Of course, in the environment is the same for monitoring air, water, and the system around us. Industry, of course, there is a need in the pharma industry, optical metrology, machine production, nanoelectronics, fabrication, and so on and so on. Another important field is the food inspection. To inspect the quality of the food, it will be good to have miniature device where maybe everybody can use, or at least can be used for larger number of people, so that the food can be inspected in variety of ways: quality, agricultural crops, pathogens, pesticides, fraud, and so on. So as mentioned, the cell phone is an ideal platform for miniaturization. And there are many works emerging almost each week, showing variety of applications of small sensors connected to the cell phone, or even using the cell phone itself with some additional software or application that is written within the software. And of course, we have the display, we can store to the cloud or send wirelessly. This is one example where we have this analytic instrument, and you can connect it to a camera of the cell phone. You can have the light coming from the LED, can be miniaturized coming through even a fiber or fiber coupler. There are a variety of options. So optics in general provide us with many possibilities, and that's another reason why we should be working on photonic devices for biosensing, diagnostics, and so on. I mean, there are many parameters that come with the optical beam, frequency or wavelength, phase, angle, so we can measure a signature, which is intensity, let's say, spectrum, and we measure its shift of certain peak or deep, or we measure the phase, and sometimes it's better to do that because the phase associated with the resonance, for example, has a sharp variation, and therefore it gives us better resolution. There is a list here of variety of techniques, and there are more. Ellipsometry, polarimetry, absorption spectroscopy, elastic scattering, SPR, fluorescence, Raman, guided wave resonances. In general, evanescent waves that can come in variety of ways. SPR is one of them. Of course, interference. There are many biosensors based on interference, where we measure either intensity, phase, sometimes wavelength. Sometimes we look for the change in the intensity, change of polarization. Lifetime, for example, with fluorescence is important. Polarization, and so on and so on. With biosensors in particular, as we know, it can be miniaturized because we talk usually about either a small sample or can be done maybe through skin, through the eye, and trying to monitor certain analytes with non-invasive methodology. And you need the optical effect, which shows sensitivity to that particular parameter that we want to use. Usually want to detect. So usually with biosensors, we want to detect either say yes or no, that the pollutant exists or not, or also maybe able to measure concentration. In all concepts, in fact, it is possible to miniaturize these devices, having an optical effect coming from a chip, for example, which is a small chip, and the detector attached to that chip and send us the information. That's a very miniature sensor. As a researcher, I work in a variety of fields. It's kind of applied multidisciplinary research. The first one is liquid crystal devices, for example, tunable filters, polarization control devices, SLMs, tunable lenses, and smart windows. And I try to combine them with optical imaging, for example, spectral imaging, polarimetric imaging, or even 3D imaging, what we call full field OCT. And of course, in optical biosensing, the main techniques we are using are plasmonics. So we use nano-plasmonics and also propagating plasmons, which is not really nano, and surface enhanced spectroscopy such as Raman and fluorescence. And we also develop the applications. So this is one selection of some of the liquid crystal devices, just to give you an impression what we are doing. For example, a polarization control device which can rotate the polarization continuously depending on the wavelength. And we can also have kind of a chromatic type device. I will talk about it later. Tunable filters, we can provide tunable filters with more than 80% transmission, can be as narrow as few nanometers. And there are a variety of concepts which we developed. They can easily be attached to a miniature camera or even a cell phone, Here we used both these devices in building a module for skin cancer detection. It is miniature, it can be miniaturized even more, and we're still working on it. Here it shows even results of some data we obtained in a clinic showing some correlation between this parameter, local contrast of skin moles, and whether they have cancer or they are normal, simply by measuring actually several wavelengths and many polarization states, then doing analysis of the obtained images. Here we show some additional devices. I will not go into details on all of them. This is kind of a single pixel infrared camera, which we are trying to develop. And it's based on combination of liquid crystal with a single pixel photosensor. So the IR image imprinted on the photosensor translates into voltage variation on the liquid crystal, which can then be read out using a visible light beam. So in fact, you create a relatively cheap infrared, could be even thermal camera, and we are working to improve its functions, resolution, sensitivity, and so on. This is kind of SLM using small number of pixels, and it can function inside imaging systems. For example, here is shown for increasing the depth of field. This is another spectral device which uses a very simple liquid crystal retarder, what we call, but it has to use a lot of processing called compressed sensing, because of the simply take the data that you measure with the device and analyze it. You can extract the spectral information with a very high resolution. That's another example of even with trying to commercialize them as a tunable filter and polarization control device based on tunable achromatic wave plate, which can tune between different retardations over a wide range of wavelengths. So it's very useful for face imaging, polarimetric imaging, and so on. And we demonstrated that on a variety of cases. Another concept we have been working on is to try to do the face imaging not in serial, in changing the face, not in serial way, but doing that in parallel. As I mentioned before, there's something called face mask these days. But that face mask, when you put it on a camera, it will get the three phase or polarization images, but then it will affect the resolution because the number of pixels will be less. Here we use this approach where we use 3 cameras or 3 detectors, and each detector will be detecting the image at one particular face. So we get the face image simply by combining very simple algorithm. It's a very fast methodology, limited mainly by the electronics. And we demonstrated that on a variety of structures. For example, these are trenches in silicon. Not sure why they are not working. Should be videos. So this one is a trench of 3.2 micron. Maybe later, this one is 25 nanometer height. And you can see that in 40 frames per second. Okay, we'll go on. So now I will get into the main topic of the lecture, which is related to the product that we are trying to commercialize. within the company Photonic Sys. It's based on a plasmonic sensor. And as you know, plasmonic sensors are based on two main types of plasmons. One is called extended SPR, and the second one is localized, where the extended happens at the surface of continuous film of a metal, and adjacent to it there is the liquid, and we want to measure refractive index basically, which is proportional to the concentration of analytes inside the liquid. So we look for some signature, and we look for a shift in the resonance, or for intensity variations or other parameters. With the localized SPR, it's mainly happening with nanoparticles, and there are several differences between the two. We will not go a lot on the physics, but on the performance, the field here penetrates a few hundred nanometers inside the analyte, while here it's very near the particle, only within 10-20 nanometers. So that's why it's called localized SPR. Because of this strong localization, the field near the particle is very high compared to the one here is lower by an order of magnitude at least. However, this mode gives us higher sensitivity. The spectral one can be few thousand nanometers per RIU, refractive index units, or even more. In the angular mode could be like 100 degrees per RIU, which is a lot. While this one has a moderate sensitivity, only a few hundred nanometer per RIU. However, it has advantages because it can be made more miniature, even can be simply sitting on a chip, and sometimes we use it. It's used a lot for color yes and no type sensors based on color variations, because the fluorescence, which is enhanced when you have molecules near the particle, can change their fluorescence or color when there is a pollutant, and therefore it can be based simply giving us yes or no questions. Yes and no answers, sorry. The fact that the field is evanescent, it helped somehow. That's what's called specific. The need for specificity or selectivity of the sensor is originating actually from the fact, the fact that we have a evanescent field means the field exists only very near the surface, so we can attach an antibody or receptor in general, could be antibody, aptamers, peptides, and so on, which will catch specifically that particular pollutant. And because our field is mainly existing near the surface, this way we can make the sensor more specific at least. Of course, the issue of specificity and selectivity is almost never perfect, and in many cases sensors fail because of the lack of sensitivity, specificity. It can be very, very sensitive, but the specificity is low, so you cannot use it. So there is a need for more work actually on these types of receptors to make these sensors more specific. Another important parameter is how much is the field penetrating inside the analyte. So we talked about nanoparticle where we have only 10 to 20 nanometers, but the extended one is something like few hundred, maybe 300 nanometer in the visible range. So if we have small particles like molecules, antibodies, or viruses even, we can detect them easily because they are within this penetration depth of the field. However, once we have large bioentities like bacteria or cells, which can be more than a micron, then a large part of that cell actually is not seen by the field. And think about one bacteria and then another one comes on top of it, then you will not be sensitive to that additional one. So the end result is that your sensor might not be monotonic as you change, as the concentration is changed. So sometimes there is a need to control this penetration depth. So it will be able to measure both small bioentities selectively and also to measure large bioentities such as bacteria. We will be talking about one concept like this very soon. This summarizes selected works that we have been doing. I will mention them quickly. This one shows improvement of the figure of merit. You can see that by looking at the width of the resonance. It simply uses the spectral mode of the SPR in the present configuration, whereby adding a nano layer of high refractive index, you see that the resonance becomes narrower and the effect becomes dramatic as you go to the infrared, to the near infrared. We get here at least factor of 3 or 4 improvement in the width. And if you think about it, also the sensitivity will increase by about the same factor, which means our figure of merit increases by a factor of 10 at least. And there's another catch when the wavelength is large. So here we're talking about 1500 nanometers. The penetration depth will be around 1 micron. So it becomes suitable for bacteria detection. The near infrared, I mean spectrometers in this range are available. They are relatively more expensive, but they do exist, and their prices are coming down. So, which means using this sensor, you will be able to detect bacteria with a large figure of merit. However, we have another methodology of doing it even in the visible range and even increasing the penetration depth more. And this is done by having this structure. We call it IMI, insulator metal insulator. And as you can see here, the penetration depth can become a few microns. It has another advantage. It is self-referenced. So you can see here for this deep, this resonance is not changing as we change the refractive index. While here it changes a lot. This is for air. This is for liquids with a refractive index near that of water. And it even becomes very narrow, which means the detection limit will become much better. And there are a variety of other concepts on the way we read the signal, for example, with the angular mode. Instead of scanning the angle, we use a spectrum of angles, could be diverging or converging beam. And then looking at the reflected beam, you will see a dark line on bright background. And by detecting that line, you actually detect the resonance location with an improvement in your precision, because now you're detecting, it's like detecting the deep, the resonance at using many angles, using many scans. The number of scans will be the number of columns here of the camera. So the number of pixels, okay, will improve the fact that we have large number of pixels. It improves the detection limit. Simple calculation shows that it improves by square root of the number of pixels -1. And we applied that to many, many applications. I will show you later a miniature system based on this concept. We're also working on kind of chip type devices, which can be even more miniature and maybe read with a cell phone. These are based on gratings, a variety of grating structures. Here we use what's called the enhanced optical transmission through nano slits or nano holes, with the advantage of being self-referenced. As you see here, again, this peak is not shifting as we change the refractive index, while we get high sensitivity as with this other resonance. And the physics behind it is can be easily explained. Simply because the grating is thin enough, you are able to excite two plasmons, one on the bottom of the grating, one on the top. And the one on the bottom is not sensitive to the analyte because it's far away. So it can be used as a self-reference device. The same can be done with the electric grating, and metal layer doesn't need, not necessarily a metallic grating. Okay, this is the proof of this concept that we talked about of controlling the penetration depth, and we can control it by changing the wavelength, something that you cannot do easily. For example, with total entire reflection, the penetration depth, like with TIRF spectroscopy, you cannot control the penetration depth by changing the wavelength, because the variations are small, at least within the visible range. I mean, it scales almost linearly with the wavelength, so you cannot see big variation. However, with this effect, this structure we talked about, you can see here between the green, where you get like 200 or 300 nanometer penetration, and the red, you get few microns penetration, which means using the same device, you will be able to detect small and large bioentities, and it's also self-reference sensor, so it has variety of advantages. Here it shows this, even this methodology of using a single laser diode with a camera, even a cell phone. This one is for air. As you see, this is the resonance corresponding to this. And this is the self-reference, the one that is not changing. As we start to put liquids, this one shifts, it becomes very narrow, even difficult to detect, but you still can detect it. And because it's very narrow, you can detect it very precisely, so you get higher resolution. So miniaturization is the main issue. As we know, there are very large SPR systems, although they contain the computer maybe inside, the robot, and maybe many ability to take many samples, like 16 or more, but still the form factor is very large. Here we managed to get it down. The first product was like 12 centimeter height, and then we squeeze it into 5 centimeter height. It's less than 1 kilogram weight. It has 2 channels. It can be connected to a pump, and I will show you some of the performance of this device. It has an interface where you can calibrate the device, you can see the results and monitor refractive index or concentration over time. I hope this video will work. Yes, this is showing one example of concentration variation with time and monitoring the variation of the refractive index as the concentration changes. Then when you start washing at some point, it will go down to the same level where it started, which is for water. So this was, I think, glycerol in water, and variations here, as you can see, less than 1%. Okay, move on. We use this system in a variety of places, a variety of researchers are using it. We do have a project now that to detect COVID-19 and then bring it to a level where it can be acting as a POC device for coronavirus detection. We're also working on Nano-Plasmonics, as mentioned. The main structure we concentrated on is columnar structure of metals, mainly silver, prepared by oblique angle deposition, so we got large area quite easily. And with that, we demonstrated fluorescence, enhanced fluorescence, and we demonstrated bacteria detection with it, glucose, and so on. And the second spectroscopy is Raman. Using a miniature instrument, you get a very large enhancement. We estimate it to be something like 10 to the 8. And we demonstrated here bacteria sensing and a biomarker in water for as a EDC biomarker for endocrine disruptors in water. Another modes is to enhance this enhancement further, and this is by exciting the localized plasmons in a nanostructure, not from free space, but first exciting the extended SPR, for example, from a prism, where we have a first enhancement of the field, and then the LSP will be enhanced even further. We can do that with a variety of modes, using a waveguide, using a grating or fiber, and so on. As we mentioned, if we have a excitation from free space, the enhancement factor is well known. However, as we excite from here, we expect to have enhancement, which is the multiplication of the two enhancement factors, first the ESP and then the LSP. In reality, we get even more than that. As you can see here, we get enhancement of the field by around 10 to almost 10 to the 6, while usually in a particle is something like 1,000 at most, and in the extended SPR is only like few tens, but when you have the multiplication, you're getting 1,000,000 or even more. And the good thing about it, you can combine it with the extended SPR. So you have this configuration for the standard SPR. And you can also measure spectroscopic signal, which is enhanced a lot due to this coupling between the LSP and ESP, and these are experimental results confirming this prediction. So with this, I think I thank you, and if there are any questions, I will be glad to answer.
More memories, explore new things, to better understand our world. One of our main challenges as researchers is access to high-quality equipment most of the time. This equipment is very expensive and unavailable to us, and we must rely on solutions that don't always precisely address our needs. Meet the SPR-H5, a revolutionary device made by PhotonicSys laboratories for chemical and biological sensing. This device is based on the excitation of a plasmonic electromagnetic surface wave, and hence can easily measure the refraction index of liquids, gases, and solids. H5 can measure very small concentrations at the scale of nanograms per milliliter and even less. H5 can measure binding kinetics between molecules, leading to the discovery of drugs and chemical and biological processes. In addition, specific pollutants can be detected by connecting a receptor molecular layer known as a lipid layer to the specific pollutant you are interested in detecting. From now on, using H5 allows you to analyze and read material much more accurately. You can measure solids, liquids, and gases by using the same device. H5 allows you to control the depth into which the electromagnetic wave can penetrate the medium that is being analyzed. In this way, you can detect even small-scale pollutants, such as molecules or viruses, as well as large-scale ones, such as cells and bacteria, all in the same device. Currently, H5 is the smallest ESP-LSP sensing device on the market, only 5 centimeters high. It's mobile and can easily be placed on your workbench. The price of H5 starts at only $4,800 and offers the precise analysis that until now was only available when using bulky and expensive devices that cost tens of hundreds of thousands of dollars. Its price, mobility, and ease of use offer a vast range of uses for this device in research laboratories, teaching laboratories, field experiments, developing specific detections in clinics, integration with other devices, and many more uses. H5 was developed at PhotonicSys laboratories by international known researchers after years of experience gathered through working in laboratories and familiarity with the daily needs and challenges facing researchers. For further information, visit PhotonicSys website at www.photonicsys.com.